Hi, so today we are going to be talking about RAID, which stands for Redundant Array of Inexpensive Disks. So, what is RAID and why was it, why do we have it? So, basically, the problem with having a disk is that if you have just one single disk, right? This can potentially cause problems because, well, you have just one disk which is doing, all of your IOs, and it can be very, very slow because a single disk is handling all the requests and it must take care of everything, right? And then it's also limited in its capacity, right? So in terms of hardware, it becomes more and more difficult to increase the size of the disk or the capacity of the disk without having it be too large, right? We there's it also is just more expensive to develop single disks that can hold more and more, right? So in terms of just one disk, it can be difficult to have that much capacity, so it's limited in that regard. And then it's also a single point of failure, right? If this one disk, something goes wrong, I don't know, if something happens, you immediately lose access to all of your data that was stored here, and it's down. So to solve this problem, RAID was made, right? It's, as the name says, it's a redundant array of inexpensive disks. So instead of trying to focus on making this one disk bigger and increase its capacity and make it faster, what you can do is you can instead use more inexpensive. Inexpensive just means smaller capacity, and yeah, just smaller disks, and just use more of them, right? So for RAID, you could have 1, 2, 3, 4 disks, which operate as a single. Logically, it would appear as one disk, but underneath the hood, it's really just 4 disks, right? So there's multiple ways RAID can be done. So there's this model of RAID 0. So let's again assume that we have 4 disks. So RAID 0, or well, all of them use striping as a means of storing their data. So this just means pretend you have an array. It's 0, 1, 2, 3, 4, 5, right? So when you store it in the disk, right, instead of doing 0, 1, you would sort of spread it across. So you would have 0 here, 1, 2, 3, 4, 5, and I'll just do 6, 7 here, right? So they're not, so if you are trying to read from a single disk, right, you're not going to find data that's sequential because of the way that it's distributed across the disks. You can sort of implement chunking if you would like. Chunking, which is sort of when, I'll just redraw it, where you can ensure that your data is together. Oops, it would be better if we did it in 4s. I think that would make more sense. You could have it so that you can have 0, 1, 2, 3, 4, 5, 6, 7. So this is a data chunk, right? You want two values to be grouped together in one disk, right? And then here you can continue. So you're doing striping, but in pairs this time, if that makes sense. So once you get to 6, 7, you would do 8, 9 here. So again, it's not entirely sequential, but you parts of it, whatever the chunk is sequential. So that's one option for RAID 0. So the problem for RAID 0 is well, let's just go through our little checklist, right? It solves our problem of the slowness problem, right? Because if you get a request for disk for value 3 and something for 0, one disk can handle that, the other disk can handle this. So this definitely helps with the slowness problem, right? Limited capacity, now you have 4, right? So if you had just one of these, you could have stored 2 values. Now you can store 4 times as many, so it helps with capacity, right? But what about failure? What happens then? What happens if, say, this disk were to go down? We have access to these 3 disks, right? We have values 0, 1, 2, 4, 5, 6, but what happens if you want to access 3, right? What happens? And that's the problem with RAID 0. It doesn't allow you to recover from failure because there's only one copy of all the data. So moving on, we have RAID 1, which tries to improve based upon that, right? So again, we have our 4 disks, except this time we are going to try and fix our problem about failure. We don't want failure this time, so what are we gonna do? We're gonna have 0, 1, 2, 3, and now for our second 2, right, we're gonna have it contain the same set of data, 0, 0, 1, 2, 3. Basically, we're splitting our disks so that we have a copy of 1/2 of the data, right? We are ensuring that if this disk goes down, if one of these disks go down, we will still have another backup copy, right? So that's really the whole intention behind this, and it does help solve our failure problem because we can hold up to n divided by 2, assuming n is the number of disks. You can have up to n divided by 2 failures, assuming the 2 failures are not the two copies, in which case that kind of defeats the purpose. But a maximum of n divided by 2 failures, and a minimum of 1. So it can handle failures, right? But what's the problem here again? So now our capacity is essentially half of what it used to be. Our capacity here used to be 4, right? We used to have 4 disks. Here we're back to 2. And this is only a slightly better option than just having a single disk, right? Like this is not the way to go. So, and the slowness is somewhat fixed. Now that you have, like, you know, two disks that can do reads potentially. You can even use the backups to do the reads, right? But your capacity is really limited. So in an attempt to fix this, we have RAID 4. So if this is just a quick graph, like if this is capacity and this is reliability for failures, right? Ability, failure. RAID 1 would be somewhere up here. RAID 0 would be somewhere up here. Now RAID 4 sort of tries to do this. It's not quite as failure resistant and it doesn't have quite as much capacity, but it tries to sort of get the best of both worlds. So RAID 4. So RAID 4, basically, you're gonna have, keep drawing our 4 disks, right? So basically, it's going to use something called a parity bit. You can sort of, so basically, in terms of like binary numbers, right? If you have, this basically tells you the number of 1 bits there are. So for example, if our number is 0, 1, 1, 1, this is our binary number, right? And the question is, what is the parity bit for this binary number? You're going to count the number of ones that you have, 1, 2, 3. If it's odd, if you have an odd number of ones, you're going to assign it a value of 0. If it's even, you can assign it a value of 1. You can do vice versa also. In terms of implementation, it does not matter much. But this is what parity means. It basically is counting the number of 1 bits, right? So what we can have here is, so when this is 0, here there's 1, here there's 1, and then this one has 1, 0, 1, right? So the parity bit for both of these, since it's even, is 1. So this last disk here is going to store the parity of every single row across all disks. So this is like the parity disk, right? And now this gives us a little bit more freedom whenever failure occurs, right? So for example, say this disk goes down and you want to know what value should have been here, right? So you count the number of ones and you go, oh, there's an even number of ones, which must mean that the one missing must have been a 0. Because if this had been a 1, then our parity would have been 0, but since it's 1, this value here is a 0. And the same thing occurs here, right? If this one goes down and you want this value right here, you have a 0 and a 1, which means the parity is odd, but in our parity disk we have it saved as 1, which is even, so that must mean that the value that's missing is 1, right? So this can tolerate failure in any of the disks, and this parity disk will be able to recover. Or even if this parity disk goes down, the rest of them should be fine on their own. But what is the max number of failures for this? A maximum of 1 node can fail, right? Because say this node goes down and this node goes down, and you want to know what the value here is. So technically there's 0 ones and the parity is 1. So technically this is even, right? So we have no idea, like, is there a 0 here? Like, are these both zeros or are these both ones? We have no idea. So that is the problem with RAID 4. And then the other problem, the capacity is not bad, right? And capacity is n-1. Basically, you can store up to 3, just one of them will be reserved for parity. But then the problem is about latency, right? How slow is it? So basically, every time you want to modify something in the disk, like say you want to change this 1 here to a 0, right? You're going to have to update the parity bit as well, the parity disk as well, to 0, right? So this means you have to do 2 writes, right, to whatever the original disk is and the parity disk, and this might end up being a bottleneck. And that's because you have to modify every single time, and you sort of have the same problem that we had with a single disk, where one single disk had to manage everything. You're all of a sudden putting that burden on this parity disk. While these might be able to, you know, do 2 things at once, like get data from both of these and write to them, the parity disk needs to be updated as well. So this sort of has like the single disk problem that we had earlier, right? So we were able to solve the failure kind of and the capacity kind of, but now slowness and latency is a problem. So now we're going to move on to RAID 5. And this is the last one that we're going to look at, right? RAID 5 is somewhat similar to what we did with RAID 4, with one difference. So this time let me do 3 rows. So instead of having, or I should have done 4. Okay. So instead of having this parity bit be stored in a single disk, we're going to have it by row. So let me explain. This is disk 1. So this will store the parity of row 1 in its first row. And this is disk 2, so it'll store the parity of the second row. And this is how it works. So if the data here is 0, 1, 1, this disk will store the parity here as 1, right? Now, the rest of its rows can be allocated for storing data. So this can be like 0, 1, 0. And now the second row is this disk 2's turn, right? So this is its parity bit. This is the parity bit for row 3, and this is the parity bit for row 4. So by distributing it, you're reducing the burden, right? So you can have faster access, and you can, and then this stays the same. Capacity is n-1 and max 1 failure. So yeah, that was great.